Get started. Let me jump back to the iPad. Okay. And we're going to start off with, I need a couple volunteers. Don't all raise your hand at once. Okay, in the back, come on up. I would like you to give me your best fit line through these points.
Oh, joyous.
We're going to have a little competition here. There's no rules. You can do whatever you want.
Okay.
No pressure.
Let's say something like this.
Great. All right. All right. Who thinks they can beat that?
Sure.
Yes, Christopher, come on up.
Are we looking for kind of a linear regression or?
Whatever you want. Listen to your heart. Oh.
Never mind. I don't actually know how to use that.
Yeah, just
I'll just do it for you.
you gotta, yeah, freeform it. Okay, nice straight line. Okay, how about one more? Who thinks they can do better than these two? Come on, I know you're itching for it. All right, Grant, come on over. Give us your best line. All right.
Okay.
Okay, you got a yellow one. All right, cool. All right, now let me give it a shot. Okay, here we go. I would like you guys to raise your hand if you think the red line is the best fit. No pressure. No? Okay, who thinks the what do we do first? Blue line. Raise your hand. Anyone? Green line? Okay, green line, yellow line. Wow, we have quite a big majority there for our yellow line over there. Okay, interesting. So, why are you guys so sure it's not my red line? What makes you think? What makes you guys think that the red line is not a good fit?
I guess we're assuming that you're showing us all the data.
Well, I'm showing you some data. I mean, I'm basically asking you for the best fit through these points here.
Based on these points,
So, okay,
majority is
well, you guys all seem to be very sort of, you have it seems to be very clear that there's a higher preference for one line than the other, right? And so what is it about the yellow line, let's say, that is causing you guys to think that that's, let's say, better than the red line? Yeah.
In terms of weight by just number of points that are represented by each line, the yellow one seems
What does it mean that a point is represented by the line, though?
like, for example, in terms of the spatial distribution of the points,
Okay.
the yellow line aligns more with the greater number of points than the red one that is just arcing above all of them.
Okay, so let me maybe try and reiterate what I think you're saying, which is that the yellow line is closer to the points than the red line on average. Yeah? Does everyone kind of agree with that? That's kind of the basis of your decision, that the yellow line is closer to the points, right? Does everyone agree with that? Okay, well, in that case, let me give you the truly best fit line. Okay, we'll go right through all these points right here. Okay, great. So, who thinks the black line is the best fit line? Yeah, come on. That's your metric. You literally said, guys, goes through all the points. I fit your criteria for the best fit line. Right, okay. So there's like some intuition that is like screaming at you, right? That, hey, there's something weird about this black line. So, our class is going to be essentially trying to like quantitatively represent these intuitions that you guys are having. Okay, and so we're going to start with kind of the most basic. I think people kind of naturally will jump to this straight line, right, being a representation of kind of how we fit through a bunch of points. It doesn't have to be, right? I could do maybe a slightly more reasonable thing where I do something like this, right? And maybe that would end up being better than that yellow line that you guys all agree on. But maybe not, right? And so we're going to take that intuition that you guys have, we're going to try and quantify it, and we're going to build up from going from this yellow line to maybe this a more complicated black line, and sort of along the way, we're going to think about why a line like this, doesn't actually necessarily make sense. Okay, and so the general principle for or what we call this, right, and I'm sure you guys have all heard of this, is regression. And so this is modeling the relationship between variables. And amongst all of these, in this particular case, it's just understanding between the x and y. And we are going to really dive down into thinking about which of these lines is best and why. Okay, so let's forget about all these weird curvy lines for a second and think just about linear fits, okay? And so we don't need to worry about this weird stuff that I was drawing right from the outset. We can have a better way of thinking about this, which is, you just redraw a bunch of these points. Okay, so when I draw a line through all of these guys, one of the objective ways that I can figure out which linear fit is best amongst all the different possibilities, right? Whether it's, that green line or yellow line or whatever, is I can actually go in and literally measure the distance from each point to that line, okay? And so this is an objective measure of the best linear fit. And we do this by minimizing the distance. Okay, so raise your hand if you've heard of OLS. Yeah, and so what does OLS stand for? Yeah, ordinary least squares. Yeah, so this is ordinary least squares. And all that means is that I am taking those distances and I'm squaring them, and when I sum all of that up, I want the smallest possible value, right? And if I change the slope of the line, the sum of those, what we're going to call errors or residuals, we want that to be the smallest value possible. And that's our metric for the objectively best fit linear line. So why do we square it, by the way? Does anyone know why we do that? Yeah.
Because if we're below the line, the distance would be negative, and then if we add them up,
It would cancel out.
they cancel.
Yeah, exactly. So squaring it is a way that we can add up the errors as opposed to having errors cancel out. Yes?
So why don't you just take the absolute value?
That was my next question. Why don't we do the absolute value? Yeah.
Penalize the further away one.
So that is true, but is there an objective reason why we would actually penalize things that are farther away?
They're outliers.
Yeah, well, we'll talk about what outliers are. I mean, they aren't necessarily outliers, right? Like, this guy is farther away from this, but would you necessarily call that an outlier? Maybe not. We will get into what you might consider an outlier from a more objective point of view later, but that doesn't. But even if a point is an outlier, right? From an objective standpoint, is there a reason why we would want to treat it differently? And I would venture to put forth that maybe not, right? So is there a good objective reason for using squaring as opposed to absolute value? So it turns out actually not really. We can do absolute values instead of squaring it. But the reason why we do squares is because the analytical solution to getting that minimum value is actually a lot easier. And so way back when we first started doing linear regressions, many decades ago, we didn't have as good computing power, right? And so it's actually almost an artificial reason that we use squares as opposed to absolute values, having more to do with the fact that computationally squaring and getting the solution when you do the squares is actually substantially easier than an absolute value. I mean, nowadays, not really, right? You could do an absolute value as opposed to an OLS, and your computer would be able to do that. But back when we actually cared about that computational complexity. So that OLS is an artifact of computational complexity, and not like, there isn't like an objective reason why OLS is actually better than doing absolute value, okay? So we'll say can do absolute value, but analytically more difficult. Okay? And so that decision has kind of retained its momentum, and people continue to do OLS today. Any questions or confusions about any of this? Okay. So we are up there essentially drawing a line through points, a straight line. What is the equation of a line? Does everyone remember from high school algebra? Yeah, ax plus b, where a is equal to the slope and b is the intercept. Ax plus b, or I think I learned it as mx plus b. Did anyone do m's instead of a's? So in regression, the standard for this, instead of doing a's and b's, we write this as y is equal to beta x I. Oh, hang on. Before I do that, I'll do beta plus alpha. Yeah, so let me think about how I want to explain this. Okay, well, we'll just start off right like this. Okay, so I is the ID of each point. Beta is the coefficient, the beta coefficient or slope. And then this guy alpha, or intercept. Sometimes you may see this written as beta 1 and beta 0 as an alternate common nomenclature. And then here is the unobserved error term. I don't know why it's doing that. I think it's the new Apple like note detection technology or whatever. Okay, so for folks who have taken some kind of regression class before, there are a bunch of different forms that that might be kind of popping into your head, right? And so let me write these out for a second, and let's go through these and make sure we really digest them and everyone's on the same page and we understand what's going on, right? So you've also got an equation y equals beta x plus alpha. You've got yi equals beta xi plus alpha plus epsilon I. That's what I just wrote here in the first one. And then we've got yi hat equals beta xi hat plus alpha. Okay, so what is the difference between all of these things? Can anyone help explain this? Yes.
Are y and beta hat vectors?
So not quite. Vector notation, so proper vector notation would actually be with an arrow above.
So I think like the second equation yi, that is like the random dot.
Yes.
Which is second equation to represent this, like the random dot. And then like the third equation that is like how to use a represent dot to represent the first equation. So then comes to a third equation.
Yeah. So yeah, that's right. I think let me just reiterate what you were saying. So the very first equation in that red circle is the actual equation of the line, of our predicted line. So the red line that I drew, that's like not part of the data or anything. That is a line that's generated from running the regression and obtaining like a slope and an intercept, right? And so y equals beta x plus alpha, that will describe both the slope and the intercept of the line. Anytime you guys see a little I there, that indicates a particular point, okay? And so let me, for clarity's sake, label each of these x's with like an index, okay? So this one, I equals 1, I equals 2, I equals 3, I equals 4, and so on and so forth, right? So this would be 5, 6, 7, 8, 9, 10. Everyone follow along so far? So if I say y where I equals 3, we all know that I'm referring to this point over here. Okay, and so in this equation, in order to obtain the value of y I equals 3 from the line that I generated, the way that I would do that is to say it corresponds to an I equals 3, right? And so whatever that value is, which would be, so this is x3 and this is y3, right? So given x3, I can plug that into my equation, multiply against the slope, add against the intercept. Okay, and then if I just did that and ignore this piece, where would I end up on this line? Yes. Oh, are you not raising your hand? No. Yes.
So what the arrow I would end up exactly on the line.
Yeah, so I would end up right here, okay? Right? It's my x equals 3 times the slope plus the intercept. Okay, and I know that this is my error term for I equals 3. So if I then add this, which let's call this -1, then I would get, sorry, jumping around here. Once I add in my error term, then I get the actual value of y I equals 3, right? And so the difference between the line and that point is that error, and so when I add that error term, I get the actual point. Yes?
Why? It seems like you kind of got the point already before you did anything with the error term.
Yeah, I mean, this is the convention. There's many uses for understanding this relationship. I am able to reconstruct the y's to make sure that the math is actually correct, right? That's one thing that you could do with it. And then there's a bunch of things where we would actually want to know the values of those residuals, which you calculate by doing this, right? You're going the other way, beta xi plus minus yi, right? So I would use this equation to calculate my errors. Does that make sense?
No, not really, but you can keep going.
Okay, so working backwards a little bit.
I understand the value of recording the error term. I don't understand what's going on when you actually throw the error term back into your equation, because it seemed like the point that you, like y3, it's, I don't know, it's right on the line, it seems correct. So why throw the error term and sort of shift it off?
It's not about the usefulness of this particular equation to achieve something. It's about understanding the structure of the equation so that you know all the relationships between your y's, x's, and errors, right?
Without the error term, you just land on the line, but you have to actually calculate the actual point, you have to add the error to the line.
Oh, the actual data point that you're
Yes,
looking at?
Yes.
Oh, okay.
I think as we kind of continue working at this, the context for why we want to really have this well ingrained will become obvious. So, putting aside what we might deem as useful or useless for a second.
I'm not thinking about useful or useless, I'm just trying to understand like the why.
Yeah.
The explanation of it.
So the context of the why, I think, will come. But most important is really understanding that this equation kind of makes sense, right? That we define yi as this thing. Okay, and the last equation is with this little caret, so we call that a hat. So y hat equals beta hat xi plus alpha. And we put the little hat over things that are predicted values, okay? And so that means we should also have a hat over this guy. Sorry, I missed that. Okay, and so we have values that are predicted, our beta and my alpha, and then I can predict values based off of that for yi as well. And those will just be the values on the line. So you can really think of that being identical to the first one, But whereas that first equation describes the equation of the entire line, the third equation describes a prediction to get a point on that line. Okay, and that distinction is useful to kind of hold apart, because when you're thinking about generating predictions on the lines, you may actually be taking x's that are not in the original sort of set. Okay, and so hopefully that will become clear in a little bit. All right, any questions about this so far? All right, so I've been talking a little bit generically about this line that we generate, right? Again, that line should be the line that gives you the lowest possible error, but how do we actually go about getting the correct beta value such that the error is as small as possible? Okay, so if you were taking a traditional like statistics class or econometrics class, this is the point in which I would go and do a whole bunch of math and show you guys a proof on why a particular equation gives you the best betas. We're an applied class, we're not going to do that. Okay, so we're not going to do like proofs of that kind in here. And yeah, if that is of interest and you want to kind of further develop your skills, or you've already taken that, right? You know, there are other classes and things that you can take there, but we're going to focus on, I would say, kind of more practical uses of this, because you're not going to be deriving this proof every time you want to run a regression, right? So calculating the coefficients. And so by coefficients, I really mean as to what we've been referring to as the beta and the alpha. There are different ways that we can actually do this. Okay, and let me first talk about the way that folks who have taken classes in this area are probably most familiar with. And so that is to solve this using analytical methods. And the way that you would, so this is considered a solved optimization. Okay, and essentially what you're doing is you are minimizing the quantity, so you're minimizing the quantity yi minus beta xi minus alpha squared for all I with respect to beta and alpha, right? So that's the problem that you are solving in order to find the correct beta and alpha. We're not going to do the math. I'm just going to tell you that the answer to this is, and maybe you've seen this before, x transpose x inverse xty. Okay, so take that as a given. This is like well known. This solution to this particular optimization. The slope that gives me the smallest errors is this solution here. Any questions about that? Besides, can you prove it? Because I'm not going to. Okay, so I'm willing to bet that some of you guys at least have seen this equation before, and if you were to run a regression in R, this equation is what's happening behind the scenes in order to get your coefficient values, okay? And so we're shining a little bit of a light into that black box, but not completely, right? Because I'm not doing all the theoretical stuff. But this isn't actually the only way that you can solve this optimization. So in an analytical method, it's almost akin to me solving the equation by hand. There are also what are known as numeric methods, which is akin to, instead of solving by hand, it's like guessing and checking, okay? And so numeric methods, to solve a linear regression of this form, very commonly uses an algorithm known as gradient descent, okay? And the way this works is you solve for beta iteratively by guessing and checking. But you are guessing and checking in a quote unquote smart way, right? This is an algorithm that basically you make a guess, you step a little bit closer to the right answer, you look again, you make a guess towards the right answer, until you iteratively go towards a solution. Okay. Any questions here? No questions, really? You guys don't want to be like, but Alan, why the hell would you use a numeric method if we have the solved equation right there in the analytical method?
But Alan, why the hell?
That is an excellent question. So it may be somewhat of a surprise to you guys, but actually, if I'm dealing with large data sets and I'm trying to run a linear regression, there is actually a point at which you would much prefer to do a numeric method as opposed to an analytic method. And so when we think about kind of like big data, like machine learning approaches, the regressions that you run in large machine learning data sets much more often uses numeric methods and gradient descent, doing this guessing and checking way, rather than the closed form solution. And why is that? So it turns out when you do an inverse of a matrix, xtx, so the -1 part, that actually requires a lot of memory, okay? So it's very fast, but very memory intensive. And so if you're dealing with a large data set where you have lots of variables and you have lots of rows for every variable, that thing will explode very quickly. And at a certain point, even our modern day computers cannot handle it to run a linear regression that way. But with gradient descent, yeah, it's like slower than solving a closed form solution, but it's much less memory intensive. And gradient descent is still really, really fast, right? And so from a like computing point of view, you might be talking about, I don't know, milliseconds instead of microseconds or something like that, right? But you won't run out of memory. And so just as a word to the wise, if you find yourself dealing with really large data sets that you're trying to run a linear regression on and you are running out of memory, run it with a gradient descent in a numeric method instead of doing the analytical method. We will not be running into examples of that in this class for homeworks, but I've definitely had students work on projects before where the data sets are too large to do this. So keep that in mind if that is a problem that you're running into. Okay?
So if it's too large, we should use analytical?
No,
Or also-
numeric, yeah. So the thing to keep in mind is this -1 procedure, doing a matrix inverse, memory intensive.
Right.
Yeah. Yeah.
So if numeric methods are pretty fast and I assume pretty good, why would we bother with an analytical solution at all? It seems like numeric methods can, do things faster and might be more.
It's not faster, it's slower.
I mean, maybe, okay.
That's why. Because numeric is faster. Or sorry. Analytical is faster, numeric is slower, but analytical uses more memory. Yeah.
And I think also a numerical is technically just an approximation, so it's not the correct solution.
Yeah, that's right. So a numeric, basically the way it works is,
When we do a regression, even with an analytical method, that's an estimation, right?
no. Sorry. Analytic is not an estimation. Analytical will give you the right answer, exactly the right answer. A numeric method cannot do that. There are like heuristics that they do where there's some stuff behind the scenes that I'm not covering here, where they actually will kind of get you to the same answer as the analytical. But like strictly speaking, okay, the way an analytical method works is like this. Okay, so that's like the true point is where my helmet is, and I go, okay, take a step closer. Oh, am I there yet? Nope. Take another step. Oh, okay. Went too far. Okay, take another step here. And then essentially every time I'm doing these steps, I'm going to see how far I am based on the gradient, right? Because you want the gradient to be 0. Well, okay, I don't want to get into those details, but essentially there's a way that I can see how close I am. And you're gonna get closer and closer and closer, but because numbers are, you have an infinite number of decimal points, you can only get so close. And basically the idea is that there's a little, there's a parameter we call alpha in the gradient descent, which is if the threshold is close enough to that, then you just stop because you say, oh, I'm close enough, right? And so you never actually get to the correct answer in a numeric method. Kind of, yes. For the purposes of what we're talking about. Okay. So yeah, less precise. Okay, so let's do some R. So there's something that I'm going to do here, which we wouldn't normally be able to do. Okay. And what that is if you want to do data analysis and you get a data set and then you run a regression on it, there are all these things that you can check to see how good a model is. But you can never, and so I'm really generally speaking here, you can never know the true value of your beta and your alpha, your coefficients. You can never know the true value of the slope and the intercept. That's not something that's just given to you, right? You are working with data, dirty data usually, and you are trying to figure out in the most reasonable way, with whatever tools you have available to you, the best coefficient values. Here for these examples, we get to cheat, okay? I actually know what the real values are. And that's gonna help, I think, that's gonna help us get a better understanding of what sort of values that we're generating, how legitimate they are, and it's gonna help us interpret certain things in certain ways, okay? All right, so I have 3 lines here. Let me describe what each of these lines are doing, or maybe you guys can help me describe. So R, U, N, I, F. Does anyone, did I talk about this function? I think I did. No, maybe not. Okay, R unif stands for random uniform distribution, and the default parameters for R unif are 0 and 1, okay? And so all I'm asking is to generate 20 random numbers between 0 and 1, okay? And so if I run this, you guys will see, and I type in X right here and hit enter, you will see 20 values that I've defined as x that are just values uniformly distributed between 0 and 1, right? So I'm grabbing out of a hat randomly numbers between 0 and 1, and that's what you see here, okay? The next line, error, is R norm. Can anyone guess what R norm does? If R unif draws from a uniform distribution, what kind of distribution do you think R norm draws from? A normal distribution, yay, okay. So I'm gonna take 20 values from R norm. R norm also has default parameter values drawing from a uniform distribution centered around a mean of 0 with a standard deviation of 1. I am simply changing that so that the standard deviation that I'm drawing from is 0.1. Yes?
Wait, is run if, is that actually just R unif, R uniform?
Yes, it's not run if, it's R
Okay,
unif.
'cause I was trying to figure
Random
out
uniform and
where's the
random
conditional?
normal. Yeah, no if, it's uniform. R uniform and R normal. Okay, hopefully everyone follows so far. I now have 20 values of x, and I have 20 values in an object called error. And I'm going to generate randomly 20 y values. And I'm going to take those 20 x's and I'm just going to put, add the error to this, okay? So you can think of this as a bunch of points drawn from a uniform distribution with noise. And that noise is defined as this normal distribution, okay? So if I run all of this stuff and I get now y's and x's, let us now plot x equals x, y equals y. Okay. So, what would this look like if I didn't have the error, by the way? Yes, it would just be this, right? But I'm adding in the error. And so now it looks like this. So distributed with bits of error. Great. So the way sorry, 1 second. I just want to make sure. Okay, so the way that I run a regression in R is via a function called LM. LM stands for a linear model, and the syntax is okay, actually, I'm gonna do this slightly differently so that the syntax for LM can be a little bit more complete. So give me 1 second. I'm gonna change things up just a little bit. I'm gonna add in a data frame that I can put all of the data into.
So when you put the dot one, that's putting it into like the first column?
No, that's just the name
Oh, okay.
of the object. So here is the data frame. The name of the data frame is forModel.1. It stands for example 1 because I'm going to have a forModel.2, which is going to be our next example. So that's just the object name. And then the data frame contains 2 columns, a column for x and a column for y. And the values are here. Okay. The reason why I wanted to do that more explicitly is because when I go to the model fit, the way that we traditionally do this is using syntax like this: data equals for model.1. And imagine that you have a data set loaded into a data frame. You can put in the column names into here, into this equation, and you would put data equals the name of your data frame, and then it would just pull the column names directly from that data frame that you're inputting over here. Okay, does that make sense to everyone? So the tilde is describing the relationship between your response variable and your explanatory variable. So on the left-hand side of the tilde is your response variable. So that's the thing that changes in response to your explanatory variable, which are all the variables to the right of the tilde. And you might ask, oh, why don't we use an equal sign there, like normal people do in a regular equation? And you would then remember that, well, the equals signs already mean something in the R programming language, and we can't do that. We can't have that particular sign mean multiple things in a programming language. So yeah, the tilde is basically instead of the equals.
Okay, thank you.
Yeah. So some of you may describe it as dependent variables and independent variables, where dependent is your y and your independent is your x. You won't hear me saying that. I don't consider that to be good practice, because actually what it means to be dependent versus independent versus the context in which we use this has always been somewhat kind of inappropriate. There are a lot of kind of statisticians who take this view on things, and so I kind of go along with that, and I call x's as my explanatory variables and y's as my response variables. Yeah, just a little nuance there. Okay, so that is how we run a very sort of simple linear regression. LM is doing a bunch of things behind the scene, among which include that y equals xtx inverse times xty to solve, right, the analytical method. And so I'm gonna go ahead and run this guy, and I now have an object called model fit that contains a whole bunch of information. Before I show you what that information looks like, I can plot, so you don't actually have to recopy and paste, you could actually just do the next line, but just for completeness, I can actually plot that line that we generated from the regression, the best fit line. And all I have to do is put that model object in here, and I'm gonna do an extra parameter called col, which stands for color, so that the line is red. And I hit enter, and boom. So this line, I can tell you, compared to any other line that I drew, so in this particular case, if you all want to try and compete against this line, I can tell you with absolute certainty that your line would be worse from an objective standpoint of, if I look at the errors from each point to the line, and I added, and then I squared it and then added it all up, there is no possible line that could be drawn that would have a lower error than this one. No straight line that can be drawn. Okay, so OLS is the most efficient and sort of truest in the sense of if it is actually a linear fit, you couldn't do better than this. Yeah.
Could you say what RM stands for?
A linear model. Yeah. Okay. So if I want to get information about what that linear model generated for us, I can do that. I can see kind of the most typical type of output for a regression table via the summary function. So when you ask to summarize the model fit object, you will see this. Okay. So here are our coefficients. We have an intercept of 0.01, and we have the beta, or the slope, of 0.551597. All right. We have these things called standard errors, which I'm going to talk a lot more about in just a second. But you can see that these values for the intercept and the slope, would we say these are fairly reasonable? Yay or nay? Raise your hand if you, this value and this value. So raise your hand if you think these are reasonable values. Okay. What makes you think that they are reasonable? Yes.
The standard error for x is a lot smaller than that.
Okay. Yeah, so that's kind of correct. You're jumping ahead a little bit in terms of, we're getting an interpretation of these and what they mean. But actually, in this particular case, so I think people who are familiar with regressions would kind of leap to that. And that is reasonable to some degree. But actually, what I'm looking for here is maybe a little bit, I don't know, more or less intuitive. Maybe less intuitive in the sense that this isn't normally something you would have access to. Yes?
I noticed that it's because the standard error is smaller than the standard deviation.
No, well, kind of, but actually it's a lot simpler than that, which is like I know the true value of the slope, right? Normally you would not know this. You would not have access to that information. But in this case, I'm kind of like, I am able to actually dictate what the true value of what's the slope is, which is 0.5, and the true value of the intercept, which is 0. And I can see that, okay, well, we're going to talk about this in a second, but I can see generally here, these values are pretty darn close to what I know the true value to be, okay? And so, without knowing the true values, what else would I have to go off of? And that's what we're going to kind of talk about with what these standard errors mean in just a moment. Okay. So who can tell me what a standard error is? Or what it, well, yeah, how would I interpret this first of all? So I know that some folks here know regressions probably a little bit better, so anyone want to help explain this to me? Come on, don't be shy. So let's talk about this value and what it means relative to this. Yes.
Is it the sum of the errors divided by the number of points that we have? Or am I?
You're on the right track. Is it the sum? Yeah, formally speaking, that's a piece of it, but not everything. Yeah, I'll write the equation in just a second. Yeah.
Not sure if it's true, but is it the average error if you would put a line to any 2 points, there, and then your average error of the slope, basically?
So if I put yeah, kind of, except it's not necessarily an average. You do like a squared and then square root of the whole piece. But yeah, okay, but that's mathematically. So mathematically, that's kind of what it means. Qualitatively, standard errors are a way for us to indicate how precise the estimate is of the mean value of the coefficient. So in other words, you can actually think of x of the coefficient of x as a distribution, okay? And that distribution has an error parameter that describes how often that value is going to be different from your estimate, okay? So let's think about what that means in practical terms. It means maybe the slope is this, but it could be wrong, right? Maybe it could be like that, maybe it could be like that a little bit, right? And think about what that would mean. Let me actually draw something. So I would like you guys to think about what it would mean in the context of these two graphs. I'm gonna have something like this. Okay, and then I'm gonna do so maybe pretend that these are the same line, basically, and that the points over here are the same as the points over here, but they're just spread out a little bit more. Now, if I were going to get rid of one point, right, that will cause the line to wiggle a little bit when I run the regression again, right? So does the line wiggle more if I take out that point, or will it wiggle more if I take out that point? The second one, right? So the certainty with which my estimate of that line of the slope should be like that actually depends a little bit on the sort of distribution of the data, right? And so depending on what the data looks like, my certainty that this is the correct line could be more certain on the left and maybe less certain on the right. And the idea is that at a certain point, maybe the slope is 0. So that's, we're going to talk about what that means in a second with like statistical significance, right? But basically the idea is that my certainty of like how precise my estimate is inherently tied to the standard error of that estimate. Okay. All right, I'm gonna write the equation just for reference. It's like not something you need to memorize or anything, but if you want to calculate this manually for a class that's not this class, you would do it like this. The sum of, yeah, that's written as a sigma. This is for a linear regression with two parameters with a slope and an intercept. It would be slightly different for a regression that has more variables. Okay, so that's the equation of to calculate a standard error, not that you would need to memorize this or anything. This is how it would calculate that number behind the scenes. Okay. So if we have a beta value of equals to 0.51 or whatever that was, right, then you can actually think of this distribution that's normally distributed, beta equals 0.51, right, and it has some kind of standard errors where this would be, you know, one standard error away would be beta equals 0.51 plus sigma, and then one standard error below would be beta equals 0.51 minus sigma, right? And is everyone kind of roughly familiar with a normal distribution that, like, if you go a certain distance away from the mean, there's some probability that that number would be above or below some number would be selected within that range, right? And so if I were to really quickly, just as a refresher, standard, if this was a normal distribution with a mean, what's the Greek symbol that we use for a mean again? I'm totally blanking. Mu. Yeah, that's right. Yeah. So if you go one standard deviation up, that's like that contains like 68% of the value, something like that, and then another one would be 95%, and then another one would be so plus or minus 3 would be like 99.7%, right? And so actually, is this like familiar to most people, right? There's some chance that you would actually see a particular value in a distribution, even if it's, you know, it seems very unlikely. You know, you could have like a 1% chance or 3% chance or whatever of seeing that. And so I'm speaking of this because this is all relevant to the typical way that people interpret a standard error of a coefficient, which is talking about something known as statistical significance.
Alan,
Yes.
I guess just to be sure, the standard error, is that only relevant when you're talking about like an interval centered on the mean? If you were to think about like a different point that is not the mean, somewhere off on the right tail, does the standard error still have meaning?
Well, so it's not necessarily the mean, right? No. So standard error is in reference specifically to your estimate of the average value of the slope. That's all it is, right? It's not in reference to anything regarding like points in the data set.
Okay.
It's all about it's all relevant to your estimated value of what the slope is. Okay. So actually, who wants to explain statistical significance? Anyone? I know you all have heard of this before. Or give it a shot. Anyone? Okay. Yes.
Based on the value or p-value in this result, we can see that there is no significant value for intercept. Maybe because the value or p-value is so high. Maybe.
Yes. So yeah, we'll get into that a little bit more, but based on what you're saying, then would the value of my intercept be bad because it's not statistically significant? Interesting. So, okay, so I'm actually going to disagree with that, but I think it's really good that you describe it that way because this is the way that people most commonly think about statistical significance, which is if a coefficient that I generate is statistically significant, that's a good thing, and if it's not statistically significant, that's a bad thing, right? That we'd like generically, I feel like most people very generically think of it that way. So let's talk about what statistical significance actually means. So you have an estimate of a coefficient. There's an error, right? So you have your distribution and you have your error. And sometimes, right, the standard error is telling us how wiggly the line is. Sometimes the line is so wiggly that it becomes zero, right? At some point, it goes like this. And if a coefficient has a value of 0, what does that mean between the relationship of x and y? There's no relationship, right? And so this is why people say having no statistical significance is a bad thing, because you have demonstrated that we can't find a relationship between x and y. What if there is no relationship between x and y? Then isn't that what our model should be telling us? Right? Then not seeing statistical significance is actually what you would want to see, right? Does that make sense? So in this particular case, our value of the intercept, we say, is statistically insignificant. I'm going to talk about what that means more specifically in just a second. It's not statistically significant, which means I can't differentiate this from 0. But what is the true intercept? In this case, we actually know, right? Well, like I'm saying, I get to play God here, right? I actually have defined the true value of beta and alpha. And it's 0, right? There's no, I never put in an intercept here. And so in this case, that's exactly what we want to see. We actually want, like, if this was not 0 and it were significant, I would be like, well, that's a shitty model because it gave us the wrong answer. And we know it's the wrong answer in this case because I made it up. Okay, so yeah. So I want, probably the biggest takeaway, and I'm going to nail this home a little bit harder with a different example later on, but depart your thinking from significance is good and no significance is bad, right? We instead want to know, what does it mean when I say something is significant and what it means when something is not significant. Okay, so here's my coefficient value, here's the standard error. If the mean is 0.01 and the standard error is 0.03, remember in our normal distribution, I don't have to get very far to hit this being 0, right? In fact, it's like a third of the standard value, or even less than that. Actually, the distance from the mean value to a 0 value based on the standard error is this, 0.265. So it's 0.265 times the standard error is how far away my distance is from 0. And you can plug this into a table to get the probability that it's different from 0 in that table. And so 79.4% of the time, the value of this coefficient based on my estimate is going to be 0 or below. Does that make sense? And so in that case, we say this is statistically insignificant because we say that we can't distinguish it from a 0 value, 80% of the time. Okay, so let's look at this one. The standard error is 0.069999, which means that I would have to go 7.3 standard errors away to get this to be 0. And so the probability, based on that distribution, that this value is 0 is 0.00077% of the time, right? It's very unlikely that this will wiggle itself to be 0. It's possible, right? Anything's possible with distributions, right? But it's highly unlikely. Okay. Does everyone follow? Yeah. Let me do. I would like to try and drive this point home a little bit more. Okay, we're going to do a new example that looks pretty similar. So this is going to look very similar to our last example, but there's one difference. Which is what? What do you guys see in the code that's different between the original y versus y2? It's not squared, it's multiplied by 2. Squared would be a caret 2. But yes, the errors are larger. So let me show you what that looks like. So take a snapshot of what that plot looks like, and then when I run it, okay, the points are more spread out. Okay? Everyone follow along? Great. I put out that data into a data frame, and then I run it with an error because I like making errors. Okay, I'll try that again.
Don't you need to relay? Oh, you did.
Okay. Um, yeah, okay, well, this particular one, maybe a little not as good as I wanted, but that's all right. Random numbers, man. Sometimes they don't give you what you want. That's all right. So, taking a look here, in this particular case, my slope estimate for x with the larger errors is 0.53, and the standard error is 0.139. And here, we have 0.5 with a standard error of 0.069. So the standard error is like half the size of the standard error of the second one, right? So which model is better and why? I'm asking, you know, we've generated the coefficient values and standard errors of both of these models. And I'm asking, which model do you think is better and why do you think it's better? Hmm? The first one? And why do you think the first one's better?
We know that 0.5 and the first one is 4.
Okay. And the standard error. Okay. So the standard error is like twice as big, right? And the estimate is slightly closer to 0.5. So so that's an artifact. Part of this is an artifact of the random numbers that were chosen. Let me ask you a question. Standard error is going to be twice as big. What if the estimate were a little bit closer? Let's say it was I think in the original one it's like 0.51. Let's just say, hypothetically, that this number was 0.505, but the standard error is twice as big. Would your answer change?
So the standard error would still be bigger in this.
Mm-hmm. Yes. Yeah. So this is still you latching on to this like standard error is worse and therefore the model is worse thing, and we want to get away from that. Yeah.
The way that you constructed it, since the error is larger in the data, you're like accounting for less of the variation in the data in your model.
Yes. Excellent. So you are thinking about what it actually means, and you're not just saying it's better or worse. Like the fact that my model is not able to account for that variation is a feature of the model and what I've estimated and blah, 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 right? Okay. And that is what the standard error is telling you. But as far as if I'm going to say a model is better or worse based on what it is telling me about the true nature of the values, just because this is twice as large, it's still 0.5, right? It's still giving me the correct values. And so there's no reason why you would say the second model is worse than the first, okay? So this is a really important distinction, is that you are not making subjective interpretations of what is good or bad. We always want to be saying that a particular model, that what these output parameters mean is like something that you understand and can interpret, right? Which is exactly what she was pointing out, which is that the fact that the standard errors are larger speaks somewhat to the fact that that the data itself happens to be a little bit more dispersed, and that my ability to match up the prediction to those points is probably not quite as good. But at the end of the day, if the thing that I actually care about isn't necessarily predicting those values and it's to get the true relationship between x and y, I've done no worse in the second example than in the first example. Okay? So, you know, for some people who've done regressions in the past and are familiar with this stuff, I often find that you know, what I'm trying to do here is dissociate the way that I think a lot of folks have been sort of incorrectly taught to interpret these results. And then for those of whom this is new, I want to get you started on the right foot here, right? And so, yeah, standard error doesn't mean good or bad. It means something in particular, and that's what you guys should really latch onto. Yeah, so as far as things to not misinterpret, but maybe kind of overinterpret, standard errors is one of those that people think about model quality, right? You judge a model's quality based on the values of the standard errors. That's one of them. The other really common one is, does anyone want to venture a guess? Yeah.
R squared.
Yeah, the R squared, great. So R squared is the coefficient of determination, and that is how much variation is captured by the model. Okay, let me write the equation just for reference. Again, not something that you would need to memorize for this class. We don't have like tests or anything, so this SS is the sum of squares. So it's the residual sum of squares and the total sum of squares. So this is just 1 minus, does anyone remember what a residual is? Yeah.
Like a certain data point minus like the expected value.
Yeah, so it's the error, yeah, that I've been referring to. It's just the error. So just making sure we're all kind of latched onto the correct lingo here. It's yi minus yi hat. My true value minus my predicted value. I square that, and I take the sum. Okay. And the denominator looks very similar, but not quite the same. What the heck does that mean? Let me give you a sort of qualitative interpretation. I am comparing these two values. So this is the denominator, and this is the numerator. If I have a couple of points like so, same points over here. The idea is that I have my predicted line, and then I have straight up the average value. Oh, that's a little bit, okay. So this guy right here is y equals, beta x plus alpha. and this guy here is just y hat, the average value of my y's. And so if I take all of the errors here, like this, that will give me the numerator. And if I take all the values like this, that'll give me the denominator. And so basically you're saying, okay, I want to compare how good my line is against just a line that has no relationship, which is just the average value of all of my y's. And so when you do this thing compared to this thing, you are ostensibly capturing a little bit more of the variation in the data, right? And this is an objective means of telling us how much more variation in the data I capture compared to just saying that there's no relationship. Okay? So let's see. Okay, we got time. Let me jump back to here. If I can find my mouse. Okay. Let me see how I want to do this. Oh yeah, actually, you know what? I'm not going to do a new example. We'll just look at these guys.
So when we call the summary function on one of these models,
Yep.
which R squared should we be?
Yep. We're going to look at the beginning. We're going to talk about this multiple R squared. That's what I wrote the equation for. Is just this guy. We will later on talk about adjusted R squared. I would like you guys to ignore adjusted R squared for a second. That's going to come into play when we talk about some other features that are relevant for estimation. Yeah, so don't worry about the adjusted R squared. We will get to that later on in the class.
And the closer the R squared value is to 1,
Yeah.
the
Oh.
closer your model fits the data.
Yeah, so sorry, I didn't explain that part of it. So one of the nice things about R squared and one of the features of it, which I suspect has led to R squared being such a prolific metric of model goodness, is that it can be compared between models pretty easily. I'm not going to say always because it's actually not true, but generally we think of R squared as being between 0 and 1. It can technically be negative, but we're not going to talk about why that happens. Okay, so R squared between 0 and 1, where the closer you are to 1, the more variation you capture in the data, okay? Does you capturing more variation in the data mean that your model is better?
Means your fit is better.
Okay, yes, it may. It may.
Is there a difference between the fit and the model?
Yeah, well, I guess the model is the fit. Yeah, so I guess if you're talking about how close your line is to the values, then yeah.
Yeah, it doesn't necessarily mean that the model is better because you could overfit the model so that you hit every
Yeah.
point, but it's not the actual relation.
Yeah, so going back right to the very first example in class, my crazy black squiggly line, that would have an R squared of 1, right? Because I would have explained all of the variation in the dots. But for some reason, you guys don't think R squared of 1 is good, right, in that particular case. And so let that help drive your intuition here that R squared means something. It means something real, it means something valid. And take away from the R squared that particular interpretation, but not this piece about a model is better or worse because the R squared is higher or lower. okay? Here's our first model. R squared has a 0.75. And so, okay, well, it'll take some time for you to build the intuition of like whether or not, how much of the variation is being captured, right? But you know, generally, if you run a bunch of regressions, you'll find that like, especially in the fields that I assume most of us are in, you know, this would be generally like high, relatively high. Okay. And in here, whoa, okay, this R squared is like way worse, 0.44. This model must be not as good. Okay, and so instead, our interpretation should be, this model does not explain as much of the variation in the data, which is true. On the other hand, its estimation of the slope parameter is like pretty much correct, right? And so, you know, that is an indication, that is another indication of the quality of the model that maybe is telling us something different than the R squared. Okay. Does everyone follow along, and does anyone have any questions or comments? Okay, yeah.
So it's like in our case here, right? Like because of the fact that our inputs for X and Y, they're all random, and the fact that we have horrible or we have a low fit.
Yep.
It kind of just explains like the fit makes sense with the data input because the fact that we chose random values.
Yeah.
There is no correlation.
Well, no. There is definitely a correlation, and as the like god of the data, I have told you what that is, right? We all know what it is. It's 0.5. This is the relationship between the data, and the fact that the error term is larger in one case has not prevented the model from telling us the correct value of that relationship. It is actually telling us that there's a bunch of noise which we've artificially introduced, and it has actually correctly identified that for us. And so the R squared being low is a feature of this model actually accurately representing what we have asked it to tell us, right? And that's actually a good thing. And I would be, if I somehow did this with errors twice as large, and I had an R squared that was larger than the first case, I would think that there's something wrong with the model, right? You have a really good R squared, but the model is trash because it's not telling us what it's supposed to be doing, right? So, yeah, we're again trying to cut away the sort of subjective way people interpret these things. Yeah?
Wouldn't the way you interpret these values depend on the purpose of your model to either predict or characterize? Like,
Yeah,
if you're just trying to
100%.
characterize the data, then like any interpretation of any of these is arbitrary. But
Yeah,
if you're trying to predict the data, then
Yeah.
there is good and bad.
Yeah, exactly. So, and then this is going to get into a divergence of the way people approach data analysis, both of which we're going to try and cover in this class. One, which is more on the inference and thinking about the relationship between the variables, and the other is on prediction and trying to get your Ys as accurate as possible. And these two things will diverge in terms of the like techniques that people use to do that, and the things that people focus on when they interpret outputs of the model. Yeah, so that's going to be a big theme in this class is these two concepts of like thinking about whether I care about that 0.5 thing or whether I care about the like R squared thing, and we're going to talk about things that you can do that are better than that. Okay, now I'm getting into subjectivity, but that I think are better than R squared.
So in this lecture, we're just trying to characterize. Right?
Yeah, we're going to build up to it. There's going to be a lot of lectures in between here and getting to that. Yeah.
Yeah, I was just gonna ask, so when you do treatments such as, and maybe we'll get to this later, but when you do treatments for electroscholasticity
Uh-huh.
and things like that, are we looking to better R squared or our coefficients?
So the heteroscedasticity thing is probably more leaning towards tools and methods that we would think about for inference rather than for prediction. But we'll talk about that a little bit later. Yeah. Yeah.
In the case of we not God and we don't know that the relationship is 0.5, how would you interpret that correctly?
Okay. Very carefully. And let me, actually, this is a really good segue to my next example. Raise your hand if you've heard of the Anscombe Quartet. Anyone? The Anscombe Quartet? Oh, perfect. All right.
I love them, they're great.
I love them too, and we're going to take a look at them. Okay, so here you guys are not going to be able to follow along, but I will post this data set and everything later on. So just bear with me for a second. So this is a data set called the Anscombe Quartet, and there are 4 different sets of data, and we're going to run a regression on each of them. And here we don't actually know the true values, or I'm not going to tell you the true values. Instead, what I'd like you guys to do is to maybe interpret the model and the goodness of each of the models. So maybe doing what I told you not to do, based on some of the values that you're going to see resulting from here. Okay. Okay, so we got 4 models, and let me run through summaries of each of the models, and you guys can tell me, what your general vibe is on each of these models. Actually, let me, whatever. I'll just run it like this. Okay, summary, model 1. Okay. So as an intercept of about 3, slope is about 0.5. Here's your standard errors, and so I don't know, what do you guys think? Tell me what your thoughts are when you see this. Yeah.
I would want to see a lot of that.
Well, you don't get to see it yet. Tell me what you think from here.
Well, then I would say it's sounds good.
Sounds good. Does everyone have big qualms with this? Yeah.
Probably not.
Okay.
Linear.
It's not linear?
Well,
How do I know that from this?
it seems.
Well, actually, I might even say that. Well, look, like we have a slope. The probability that it's like that it's not, or that it's 0. That's not explaining. It's pretty low. Maybe a little bit worse with the intercept, but still below 5%. Right? Okay. These are the things that you normally think when. These days, when you interpret regression, I'm going to look at the R squared.
I think I don't
0.6.
understand why you're comparing why are you comparing things to 0 when you're considering that the probability that they could be 0? Why?
Yeah.
Why 0?
0 is our kind of reference point, because when I have a slope, right, the whole point of all of this is to figure out a relationship between x and y. When the slope is 0, it means that there's no relationship. So that's the thing that people usually gravitate towards, and that's why we have this whole statistical significance thing. And if you're like statistically insignificant, that means that there's a larger than 5 or 10% chance that the value of the coefficient is
Didn't have any effect on the.
Yeah, exactly. Yeah. Okay, 0.67. All right. So if you had to rate this out of 10, how good would this model be?
0.67.
0.67 or 6.7? Okay, yes.
6.7.
Haha. Okay, great. All right, let's take a look at model 2. All right, here's model 2. Yeah, okay. What do you guys think about this one? We got intercept of 3, slope of about 0.5. R squared, about 0.66. Not bad, not bad. Okay, probably pretty similar. maybe 0.1 lower on the ranking, right? Then, okay, all right. Okay, so let's take a look at model 3, how that guy compares. Oh, okay, yeah, pretty similar, huh? Like slope of 0.5, intercept of 3, all of our, I didn't actually talk about the standard errors and probabilities, but they're all about the same, right? 2.5% on the intercept and about 1/10 of that on this for the slope, right? So we would say that models 1, 2, and 3 are all about as good as each other, right? Okay, getting a little nervous here. Okay, model 4. Hey, look. Oh, we're pretty close too. 3.5, 2.5%, about 1/10 of that, and R squared, 0.66. So if you were doing what some folks might kind of be defaulting to, right? Just thinking about standard errors and thinking about R squared and thinking about the quality of the model, and we think about all these models as being relatively close in terms of quality. Yeah, well, so like your alarm bells should be going off, right? And thinking about, Simon, you're like, let me look at the data, right? That's what you should be doing. You should be thinking about all of these. There's nothing wrong in terms of the statistical significance, the standard errors, the R squared, they all are telling us something, right? But in the context of how good a model is, they may be deceiving you. So let's take a look at what we've actually done here. Okay, oh, I missed the critical line. Ugh. I hate that I don't have my little preview monitor here. Oh, I don't need to do that. Okay. All right, so here's the data and the fits. How do I do this again? Oh, over here. Okay, da 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 da. Okay, here's the Anscombe quartet. These are famous examples that some Anscombe dude put together that all have the kind of same results. Okay, and obviously these comparisons were not made in like good faith. They're not like fair comparisons or whatever, right? But the point of this being that the thing that you gravitate towards to tell us whether or not a model is good or not are those very common parameters that people talk about, standard errors, R squared, blah, blah, blah. You may miss this kind of thing happening. And so we want to build up a better foundation in terms of how we're gonna look at these things. We're gonna have a whole suite of other diagnostic tools to help better tell us other qualities of the model besides the very common R squared and standard errors. And so, yeah, every time people just harp on those sort of things, and the next like seminar presentations that you see, just think that they could be doing this kind of shit, right? And it would be total nonsense. Okay? Okay, that is it in terms of material for today. But before we leave, I did want to mention, so the homework 1 is posted. It'll be due at the end of the day next Wednesday, so you guys have a week and a half to do it. But you guys, you have to submit it, for anyone who's doing it in R, you have to submit it in a R Markdown format, and I'm gonna send that format to around to everyone. So I did not have time to cover how to do that in lecture, so that will be a little bit of independent learning, especially for those who aren't familiar. I will link some tutorials on how to do that, but this is a place that people get hung up on every year. So please make sure to do this a little bit ahead of time, because if you're trying to compile the R Markdown at the last minute and you're running into errors, it's gonna be a nightmare. And so, you know, go through the tutorial, do a quick example, get a little bit familiar with that, so that you're not trying to compile at the last minute. It's gonna be, yeah. Every year this happens, so I just want to give you a aforementioned warning. Yeah.
I just took a quick look at that, and I think the first one's like kind of a table, which you could technically maybe do on page or two, but we are supposed to just do it in R.
Yeah. Yeah, you could if you wanted to, you could scan it in as an image and put it in the R Markdown.
I mean, on the laptop, you could write it in the PDF document and saying the result. But
Yes.
You're supposed to just run it in R, in the R Markdown.
Yes. Yeah. Yes, that's right. Yeah. Any other questions? I will get that tutorial and a template out as soon as I can, and yeah, come to me if you're having any problems. Me or Lou if you're having any problems compiling. Yeah. Okay. Thanks everyone. See you guys on Wednesday.
Thanks.
Mm-hmm.